So welcome to the Software Computing Roundtable in December. That's the last Software and Computing Roundtable in this year. And we had in total this year 10 Software and Computing Roundtables. The recordings of all of them are available on YouTube, on the YouTube channel of the HEP Software Foundation. At the end of the year, we have our year in review event, where we share software and computing highlights from the organizers, Brookhaven National Laboratory, Jefferson Lab, and the HEP Software Foundation. We start today with Torre. Torre doesn't, as one of the hosts of the Software and Computing Roundtable, he doesn't need any introduction. I will keep it short by saying that he leads the nuclear and particle physics software group at Brookhaven, and Torre will share us highlights, both software and computing side, from our colleagues at Brookhaven in the next half an hour. I cannot hear you, Torre. You are muted. Can you unmute, please?
Oh, it keeps going back into mute. Can you hear me now?
Yeah, we can hear you.
And there, my slide should be up.
Yes. Perfect.
Okay, here we go. Thanks, Marcus. Let me also acknowledge Ofer Rin from the facility, who put together the facility slides that I'm going to show, and these slides reflect contributions and the work of many, some of whom are listed at the end of the talk. Marcus is going to keep an eye on my time because I have a lot of slides, too many, even though quite a bit fewer than last year. So I'm going to zip over them pretty fast. I won't go in deep. My scope is experimental nuclear and particle physics in the BNL physics department. It is selective and incomplete. It has more of an emphasis on software. So with those caveats, the outline is I'll talk first about the facility side, then the software, and then go through nuclear and high energy experiments we're involved in, say just a word about AI, ML, and Flash plans and priorities at the end. So starting with the facility, which here at Brookhaven is the Scientific Data and Computing Center, SDCC, and their biggest highlight of the year was that they commissioned a new data center, building 725, our original light source building. It became operational this year as part of an overall BNL core revitalization project with one big main data hall for storage and compute resources that can support up to almost 500 racks and 10 megawatts of power, with initially configured almost 200 rack positions that will start to be filled this year and will progressively continue next year. Also, fully commissioned, deployed network room hosting all the central network equipment, and very importantly for our data hungry experiments, tape room capable of supporting up to 6 8-frame IBM libraries, and configured now with 2 libraries so far. This is a flash of the main data hall, which I won't dwell on further. On the storage side, both distributed and central disk storage. On distributed storage, we use Dcache and X-root-D primarily. This year, SPhoenix joined the slate of other experiments using Dcache in production. Atlas and Dune upgraded to the latest golden release, a highlight of which is authentication capabilities supporting tokens like side tokens, something we're eagerly awaiting across distributed services. A test bed supporting quality of service, which basically means management of the hierarchical tiers of storage in development and testing. X-root-D also important, particularly for STAR, but also for others. On the central storage side, primarily GPFS and Lustre file systems, the inevitable upgrades this year for security vulnerabilities. Luster footprint expanding, and also making use of object store, S3 flavored object store for EIC and center of functional nanomaterials. So 75 petabytes overall on the distributed side, 16 petabytes, 2 billion files on the central side. In tape storage, which is based on HBSS, more than 180 petabytes now on tape, over 20 petabytes written, and 175 petabytes read and served up to the community in 2021. We saw a major upgrade of HBSS this year with new file grouping capabilities important for functionalities I'll talk about later, like data carousel. Installed two 10K slot IBM tape libraries I mentioned for Atlas that should be in production this year. Also in newer LTO8 tape technology, it's been deployed for Lattice QCD, and Star and Atlas also moving to this year. Phoenix and Archive will remain on LT06. S-Phoenix is coming, and it still has to be worked out just what library configuration and tape technology will be used for the very data-hungry S-Phoenix. In Data Carousel and WLCG Tape Challenge, Data Carousel has been one of our big R&D activities at the intersection between software and facilities, and indeed it's been a close collaboration between SDCC facilities and NPPS on the software side to give managed access to data and efficiently process data that's primarily resident on tape. SDCC playing a major role in this, and it being exercised in the 2021 WLCG Tape Challenge. All Atlas workflows but one, I think now, are run by default in data carousel mode now. It's been a very successful R&D program that has now transitioned to full production, with effort going on to optimize the utilization of tape resources, including something we're eager to add is grouping of files, related files onto tape to give more efficient retrieval through the data carousel, and those are new HPSS features being deployed that we'll be able to exploit. WLCG Tape Challenge was conducted recently, all 4 experiments, and all the WLCG Tier 1 sites participating. First of its kind, and both Atlas and BNL had a good run meeting the targets. On the network side, also data challenge there, with the 2021 target being to see throughput of 10% of what we'll need for HLLHC, coinciding with the highest rate for special periods of run 3. Targets 20 gigabyte in, 20 gigabyte out, comfortably achieved with 50 gigabyte in and 60 gigabyte out. So target reach, no special storage and network issues seen. On the high throughput computing side, SDCC operates 2,000 compute nodes, providing 80,000 logical cores. This year took delivery of another 7 racks with 210 Supermicro Xeon Cascade Lake servers, increasing the core count by over 20K. Also an update of HT Condor batch. And like everyone else, we're dealing with the Linux issue with the early end of life for CentOS 8 and options like Rocky Linux 8 being looked at. On the HPC side, BNL currently has 5 HPC clusters available through allocations upon request and justification. I won't go through them. All important ones are institutional cluster, widely used across the Laboratory for Scientific Computing, a dedicated machine learning one, and a number of others. Evaluating test units also for the next generation of institutional cluster. There's been a process of consultation in the community going on for some time that's leading to convergence on technical configuration for that. Shown there, mix of CPU and NVIDIA GPU. Jupyter, getting into the services provided by SDCC. Jupyter is a growing service at SDCC, of course, web browser-based interactive analysis. It serves as one interface for using HPC and high throughput resources. You can run notebooks on dedicated VMs, VHT Condor, Slurm Batch. Externally available, of course, and with the nice feature that experiments can maintain their own kernels. Other cloud-based tools and services, the Overleaf LaTeX editor is now a provided service, as is Jira, used by a few experiments, regarded as heavyweight by some, but very popular among others. Atlas, for example, and an in-house Git service in particular for supporting private authenticated repos, but also supporting shared ones. On the website side, website improvements during the year, improved search results, new site layout, improving user experience, and content improvements to give better guidance on the services provided, with a number of sites either existing or in development among the science communities taking advantage of SDCC. On the Kubernetes side, OKD is what we're using. The community distribution of Kubernetes that powers Red Hat. OpenShift allows using OKD-like features like Helm charts to describe deployments. Test development OKD cluster is online at SDCC, and new installations, both in terms of worker nodes and service hosting, are being tried out on this OKD test cluster. And production cluster hardware expected very soon, and we're going to put it to work right away for SPhoenix. Rihanna, very interesting development work at SDC with a testbed deployed. You'll hear also later about our work on the software side, using this in data analysis preservation as a platform for reproducible analysis, developed out of CERN, and very likely to be an important part of future HEP analysis facilities. A number of test users, certainly Atlas, I mentioned the NPPS software involvement, and Phoenix giving a lot of attention to data analysis preservation. We're integrating it to Panda, workflow management. It's being adapted to support SPhoenix CVMFS access, and available to interested parties who would like to try it out. ServiceX. ServiceX is an R&D project out of primarily Iris HEP, which is an NSF project with Atlas and CMS involvement for the very popular topic of columnar data delivery, pre-processing, pre-filtering, delivering data efficiently to analysis consumers. So this is also a test deployment at SDCC. Also maybe an important part of future HEP analysis facilities, with a test deployment in the Kerberos cluster. Okay, onto the software side, and I'm talking primarily about activities in the nuclear particle physics software group, NPPS group, which consolidates much, certainly not all, of the software going on in the physics department in high energy nuclear experimental. Currently 23 nuclear and high energy people working on a whole raft of nuclear and high energy experiments that I'll talk about, with a group emphasis of cross-experiment common efforts, common projects, sharing personnel, expertise, software. 15 of those 23 people work on multiple experiments, with many collaborations with outside, from inside BNL, like SDC itself and CSI, to WLCG, HEP Software Foundation, and the US projects of NSF and DOE, and a lot of software activities beyond NPPS, as I mentioned, are going on in the experiment collaborations, different groups around the physics department. Whole raft of collaborations you can see there. So as I get into the experiment, starting with Phoenix, where our focus is on data analysis preservation. We reported last year that work was getting underway using a very CERN flavored technology stack, which is serving us extremely well. This is becoming more and more populated during this year, with GitHub for the web, Zenodo for documents, HEP data and open data as data repository, Docker for containerization of analyses in particular, and Rihanna. This is where we're applying it to a real data analysis preservation task for SPhoenix. In SPhoenix, also we've been continuing to work in the ACTS tracking, which was in its early stages when we reported last year. There's really been great project progress this year, getting close to meeting targets in resolution, timing, memory, exercising where things are in a mock data challenge, the second one that's starting essentially right now, really aimed at providing realistic reconstruction for analyzers this time, but certainly a lot more to do still, perhaps most importantly, to integrate realistic TPC space charge distortions, which are substantial and of course have dramatic effect on the tracking. Conditions database is something where we've been drawing on activity in another experiment, in particular BEL2, where we're responsible for the conditions database. We've been taking that database based on Tomcat, based on the model a lot of us are using in our conditions database as a REST-based service, but updating the backend to Django, streamlining the schema, streamlining the tag management, making it generic experiment agnostic, and implementing a C++ interface, client interface that can be used on the SPhoenix side within their framework for accessing the database. So this is progressing now, and we're thinking in the future. This draws on work informed by the HSF white paper, which primary author of the HSF white paper being in the middle of this work. So we're contemplating maybe we should bring the outcome of this in terms of a generic conditions database back to the HEP Software Foundation as a reference implementation. So we'll be talking about that in coming months, I think. In distributed computing, SPhoenix is adopted from Atlas, the Panda workflow workload management system, the ecosystem around it, also Rutio for data management, so a stack that BNL and NPPS have a lot of good experience with. So we can give SPhoenix a lot of help in bringing this up, including new services both for Penn and Rutio at BNL. For Panda, this is an entirely new thing, bringing up a BNL service, not least because BNL wants nothing to do with Oracle, so we're using Postgres in the back end for the first time. Rutio familiar both with running at BNL for BEL2 and running with Postgres in the back end. And SPhoenix making use of a new feature of Penn of the past year and a half of DAG described workflows, which means arbitrarily complex workflows. The collaboration can be injected into Panda. The data carousel also uses that, and the data SPhoenix is likely to have to effectively process tape resident data, so the data carousel likely to be important, as well as command line tools, which we call P-chain, which exploit this capability to have an arbitrarily complex, essentially DAG-defined workflow. In STAR, databases and collaborative tools has been an area where we're contributing in database and online tools proper, a very long list of services, extending into collaborative tools, record keeping tools, the phone book sort of at the heart and center of them, extending into a range of functionalities I've listed here. Interest from other experiments in this stack. It's being used by others, and SPhoenix is interested in using it in the future. So there's been a round of re-engineering and updating of the technology stack, make it generic, make it modern for the future it has ahead in supporting new experiments like SPhoenix. In STAR, STAR is, as I reported a year ago, making its first venture into Geant 4. Geant 3 has continued to work well for them, but STAR has a forward upgrade for which the hadronic physics of Geant 4, better than Geant 3, are very important. So Geant 4 is making its entry into STAR now. Highlighted this year is the first full release in October. So this really relies on the community picking it up, doing physics validation, in particular for calorimetry. Also in STAR, it's been an extremely busy year in the software infrastructure side. They migrated from CVS to Git, driven by NPPS, and in particular GitHub, adopting GitHub workflows using designated code maintainers with defined process for reviewing and approving commits prior to merge. CI for STAR, the STAR repository has been set up using GitHub Actions, using containers in the CI process for self-contained, well-defined environments, and also using community standard tool now of SPAC for describing dependencies. Moving to EIC, simulation, a longstanding activity in support of the detector development process, which has had an enormously busy year with the proto collaborations developing detailed detector designs. With that has come a move from fast being the most important simulation flavor to full being most important. So we've had responsibility for a long time for the fast simulation EIC smear, both at BNL and in EIC software community and software working group. We've been taking advantage of the switch to full simulation to start a new software project in the full simulation called EAST, EA Simulation Toolkit, centered around Geant4, in particular the latest Geant4, and under the leadership of one of the fathers of Geant4, Makoto Asai, to be able to offer the EIC community, once they're through this terribly busy proto collaboration year, what we hope will be taken up as a common basis for EIC simulation going forward, and NPPS has been in the mix on that. Also ongoing work in infrastructure and collaboration. I think I'll go lightly on that because sort of steady state from a year ago. On to Atlas offline software. The big event this year has been approaching readiness of Run 3. Very important developments like multi-threaded Athena have had a good year and look ready for Run 3, which I couldn't really have said a year ago. We're in the middle of this because NPPS has the co-coordination of the Atlas software right now. We've led the design and much of the implementation of the new analysis model for Run 3, a major component of which is new compact analysis formats, and looking ahead to new architectures, leading the implementation of ARM in current releases, which anybody who buys a new Mac is very interested in these days. Towards Run 4 also it's been a busy year, looking at the very popular topic of applications of RN tuple, in particular for our analysis formats, and we're co-leading the US Atlas effort towards HLLHC computing, which is involved how do we use HPCs, and in particular their accelerators. The answer to that in the near middle term at least looks like machine learning. So we've have an active program in US Atlas on developing AI/ML capability in machine learning, on the training side, on the big HPCs within the Athena framework on the inference side, and targeting fast chain as the end-to-end generator to analysis format workflow, which could leverage these big machines, in which Atlas aims to be using for 90% of its simulation in Run 4. In workflow management, I mentioned Panda a few times already, and that's been a very active development area this year with an interesting focus we've wanted to do for years and years on Panda and haven't managed to until now, of analysis-directed use cases. These involve supporting the importance that ML increasingly has, and we think will have in the future, in particular HLLHC. Active learning, pseudo-interactive analysis, exploiting clouds for analysis, tools like Rihanna, and P-chain, arbitrarily complex workflows. Central to some of these is the Intelligent Data Delivery System, IDDS, we're developing in concert with Iris HEP as a HSF flavored labeled project to orchestrate workflows. Again, this is where the DAG described workflows come in. And I'll mention a Google R&D collaboration in a moment, and at least for friendly HPCs, which means anything except the DOE giant LCF machines, have had a very good year with through Panda exploitation up to a scale of the entire Atlas grid being run at that kind of scale off of a single HPC for several months, a European HPC that came online, and we exploited it early and quickly. I can't get into the Panda Rihanna integration, but this is a very interesting step that ties in with SDCC's Rihanna deployment and Phoenix using it and so on. Atlas data management, I'm going to have to skip over because time is growing late. Also software infrastructure. The Google project, I mentioned this emphasis on analysis and close to real-time analysis, and the Google project has been the context for that. It's really become a very useful and exciting R&D sandbox for these things, like Pythonic ecosystems, columnar analysis, everything to do with delivering data to analysis clients, and how do we use Kubernetes. So now finally into the last few experiments in Bell 2, we're involved in event data, its calibration and conditions data as the biggest, as the US Bell 2 Tier 1, the biggest raw data center outside of KEK, now with prompt calibration going on at SDCC. Also on the conditions database side, as I mentioned, in the context of SPhoenix picking it up, we're responsible for the conditions database there. Also in distributed data management, it's been a terrific year for that in Bell 2 and for NPPS, because we led Bell 2 through their migration in a live experiment, doing processing, if not actual data taking, I think. Migration from their old system to use of Riccio as their production data management system, which went smoothly. I'll have to leave it at that, I think. Then into Dune.
5 more minutes, Torre.
How many?
Five.
Okay, thanks. I'll be okay then, I think. In Dune, we're involved in software and databases. Software, one of the key software packages, very broad functionality. WireCell is centered at BNL, not in NPPS, but in the neutrino group at BNL. NPPS has had a leading role in the software framework requirements and design, which was recently reviewed by HSF and is now moving towards an implementation plan. R&D also going on AI ML, and a very interesting study on applying GANs to understanding differences in systematic differences between simulation and data. On the databases side, NPPS co-coordinating Dune databases, and we have our first dedicated Dune person, a postdoc, starting work on conditions database. And we're headed for CDR and Dune in next year, and we'll be participating in that. Ruben had an enormous year for us because Ruben adopted Panda after we put a lot of effort into helping them evaluate Panda. It's a really challenging environment, perhaps surprisingly, not to them. It approaches Atlas in scale, 200K. Concurrent jobs, very complex workflows. So the IDDS and the DAG support in Panda is crucial for their ability to use Panda. In light of this, we're now hiring a new Panda core team member. Advertisement, we have a position open, BNL staff position open. Let me know if you want more info on that. And this will be based on a Panda instance at Slack, also Postgres based, so fits nicely with what we're doing for SPhoenix at BNL. AI/ML, I wish I had time to really talk about. I remember being impressed by the JLab talk last year on everything you're doing in AML, and I'm sure I'll even be more impressed this year. It's been a ramp-up year for Brookhaven, which is good. You can look at the vision we put together for BNL HEP in this past year behind that link. There are some very interesting projects going on that I have slides for in the supplements, but I don't have time to go into. Our general approach we found we agree on across the department is to apply AI/ML after exhausting well understood conventional ways to extract information from data. Basically trust and leverage your accrued domain knowledge to wisely guide how you apply AI/ML where it really adds unique value and where you get a result that can be understood and trusted, including the error properties. So plans and priorities, of course, running experiments, soon to be running experiments, our top priority, and continuing to grow cross-experiment contributions. SPhoenix readiness, really the top of the list, and it's been our big focus over the last year. HLLHC readiness is the principal Atlas focus, and supporting the EIC, of course, has been a growing activity during the year. Some have really come to fruition, things that we said last year we wanted to grow. Ruben has now adopted Panda Dune. We really are participants now, so check those off. Building more AI/ML experience and activity remains a big to-do item for the future, though we did make progress this year. And data analysis preservation had a good year in Phoenix, and we would like to see attention on that from others as well. There, that's it. Thank you for your attention.
Thank you very much, Torre. This was very interesting, and you perfectly stayed on time, so even had 1 minute more. So thank you very much. And the questions are coming in. David.
So yeah, my first question is if you can help me get out from under this pile of information you just dumped on my head.
I'm sorry, yeah. Guilty.
It's very, very impressive, the number of things that you guys are involved with and what you're doing. It actually begs kind of the question to me, with so many different services and stakeholders you're trying to support, how do you go about managing the number of services that you will investigate and deploy? And do you have some other mechanism for forcing the retirement of other ones so that you keep a reasonable number of these things that you can actually manage?
Well, one way is to look at reuse, be guided by the community, and target services and tools that have traction in the community and that can be applied across multiple experiments. So we have had our own that we advocate and encourage, things like Ruzio, Panda, that we are sort of pushing out there to the community and are seeing acceptance and growth. But in other areas, like the whole stack involved in data analysis preservation, we are latching on to an emerging community standard, emerging largely from CERN, and are very happy to have it too. And the we there is pretty much SDCC and NPPS, but I would invite any SDCC comments if Ofer or someone else wants to comment there. In terms of retirement, I'm trying to think of things that we've retired. I don't know if it's good or bad that things don't.
Did you like encourage STAR to move away from CVS so you don't have to?
Oh yes, oh yes, absolutely. I mean, my own opinion is that well, it was certainly due, yeah, that kept our guy Dimitri very busy for the year, and it was certainly, well, I'll stop commenting there if someone from STAR wants to comment, but that was certainly a good move from our point of view in consolidating around modern tools.
Thanks.
Same for JAMP4, of course, but you know, if it ain't broke, don't fix it. And whether we'll see the migration of the full STAR simulation to JAMP4 in the lifetime of STAR, which goes through 2025 as far as data taking goes, remains to be seen. But it's nice to see JAMP4 in the picture now, at least for the forward calorimetry.
Wouter.
Yeah, hi Torre, that was a great overview, and I'm glad to see that you have some plans, for example, for CDB to work with HSF and make this a standard reference implementation. I have a question about these large projects. What is the sort of the viewpoint of BNL on them? For example, I note that some of the large infrastructures projects like Rusio or Rihanna that come out of CERN typically are almost developed with the eye on the outside community, and that translates in nice websites that are useful in terms of finding information. It seems like Panda is sort of at a similar stage where you're trying to get large customers or large user bases for it, but the kind of active outreach that some of these CERN projects have does not seem to be there with no website that would make it easy to get started. Does that reflect sort of a conscious decision, or can you comment on that?
Yeah, it's a good point. It's certainly true, and it reflects, I think, most of all, that the limited manpower we've had, the limited effort that we've had on Panda has really been chewed up by the responsibilities we have to particular experiments, communities, for most of which is Atlas. But we haven't had as much of a culture of building a shrink wrap tool as we should have and should have benefited from, really. We had a project, Big Panda, a few years ago with external support that helped us take steps towards that. But you cannot compare Panda with Rusio, for example, which you can pull off a shelf and have running in a week, or Dirac. Panda is something where you need to have the help of Panda experts to bring up a service to try out and play with. And of course, now with SPhoenix and Ruben joining the list, which does extend beyond Atlas and in who uses it, we are driven by necessity. Necessity finally corresponds with our wish to improve its use and how it's seen and how usable it is by others. In particular, there's been a big documentation overhaul in the past year. So this is something that we should see improvement now. For example, a year from now, a well-documented Panda you can pull off a shelf and run off of Postgres is a more realistic aspiration.
Thanks.
Thank you very much again, Torre. This was really very exciting and very impressive, the amount of information which you presented in exactly 29 minutes. So let's see next what happened at Jefferson Lab. Graham, would you like to also have a 5-minute warning?
Yes, that would be nice.
Okay, then we are looking forward to software and computing highlights by Graham. He also doesn't need an introduction. He is well known to the software and computing roundtable, and but he will present in his role as head of the scientific computing department at Jefferson Lab. Please go ahead, Graham.
Okay, so last year I did a Torre and I presented about 39 slides or something like that. So this year I decided to put the word highlights in front and try and cut down my number of slides. So firstly, apologize to people who have projects at Jefferson Lab who don't get a mention, but this is in the interest of fitting into 30 minutes. Okay. So a recap of the first slide from my talk from last year. We formed the Computational Science and Technologies division, which used to be the IT division at JLab, in June of 2020. And this was to emphasize the increasing importance of computing at the laboratory. So I took over as head of scientific computing last year and formed two groups. the Experimental Physics Scientific Computing Infrastructure Group, who focus on scientific computing related to the experimental program, and a second group, Performance Cluster, blah, 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 who focus on the aspects of computing related to theory and compute clusters. And I'll talk a little bit about both of those later. The Scientific Computing Operations is actually as part of the CNI Computing and Network Infrastructure Department, because it made more sense to put those people with the networking and system administration experts. So their focus is on the operation and hardware technologies and reliability. So the big change between last year and this year is that you see with the red shape there, we formed a data science department. This is led by Malachi Schramm. He moved to JLab from PNNL. And we've moved some staff and projects from the scientific computing department to data science where they more logically sit. We've also had some staff to work on AI ML projects funded from outside the NP program. We've also expanded the portfolio of the PC Sci group, who were mostly focused on LQCD, by the hire of Makoto Asai to work on the GEONT4 development that Torre was talking about in his presentation of Project East, specifically targeting EI simulations and use of heterogeneous hardware. And it's a particularly good group for him to join because the PC Sci group have the experts in optimization for running on GPUs. So a little bit on facility status. We've had a capacity growth to the AMD cluster this year. So we're somewhere about 28,000 hardware threads, and we run 2 jobs per hardware. So we're up about the 60,000 job capacity. One of the decisions that I made was that the procurements of machines, instead of, as you can see, when we go from 13, 14, 16, 18, we have basically a different cluster, different generation of hardware for every year or 2. So I made the decision that we would buy AMD Rome in 2019 and stick with that for a few years. So 2021 is now the last year that we were buying AMD Rome, and Farm 22 will be AMD Milan, which will give us a performance boost for the same number of nodes. The focus of the Scientific Computing Operations Group has continued like last year to be on improving the utilization and the uptime. So now the utilization is approximately equal to uptime at 95.6%. Another change that we made this year is we've now promoted EIC to the same level of the first year tree as the 4 major experiments at the lab. I should say a little bit about this. The way that we operate the first year is 90% of the total capacity of the cluster is allocated to EIC and the 4 halls, and 10% is reserved for anybody else. So for example, Theory, Accelerator, EH&S, and so on. So this was actually a big boost. EIC got lifted out of the 10% and put into the 90%. And as you can see over there, they have a fair fraction of the total now. LQCD clusters, these are allocated by USQCD. We have a 2016 era cluster, which is slowly dying of old age. And I didn't cherry pick this image, but if you look at the plot at the top right, the 16P is the one with all the orange and red on it, where orange is in maintenance and red is down. So these machines are getting a little bit past their expiration date. The highlight of 2021 is that we installed a 21G GPU cluster. This is 8 nodes, each with 8 AMD MI100 GPUs. Inside a node, the GPUs are connected over the AMD Infinity Fabric. I'll say something about that on the next slide. The use of AMD gives us a gateway into some of the leadership class machines that have AMD GPUs in them. So PC Sci Group, I said one of the things they work on is GPU LQCD optimization. So the LQCD code spends a significant time in tensor contractions, and these are challenging to optimize, to parallelize. The reason for this is that the operands for generated propagators are distributed across several nodes. So communication time between nodes becomes dominant. So if you can cut down the number of nodes you have to communicate across, you get an advantage. The second part is that the operands for the quark propagation diagrams are quite small, so that the host device synchronization overheads limit the overall performance because you're trying to do a lot of small things. So the accomplishments for this year is we've improved the performance of the tensor contractions for CPU and GPU on the critical paths of the workflow. And we've demonstrated a competitive performance of tensor contractions on AMD GPU MI100s that's comparable with recent NVIDIA, such as the A100. And if you look on the right, the center chart tops out at about 60 gigabytes per second over this InfiniBand fabric within a node. So this is the big boost that we get by having 8 GPUs in one node connecting this way. And if you look at the top chart, sorry, the bottom chart, 48 GPUs from 21G cluster is about a third of the performance of 48 GPUs in the Perlmutter leadership class machine. This doesn't sound too great, but we're continuing the code optimization, and we expect to close this performance gap so that we'll have a cluster which is a really good surrogate for running on the leadership machines. So facility status, internet facing and grid services. This last year, we've made rapid improvements to the OSG services for JLab. We've added 2 submitter hosts, redundant collectors, and we're now able to run OSG jobs. So you can submit a job at JLab or Brookhaven and have it land on JLab clusters. EIC has its own XRootD server, as does OSG, and these are both 100 gig capable data transfer nodes, and they were supporting offsite production services. Unfortunately, Globus is only running on legacy hardware, which is 10 gig capable. We've ordered new 100 gig hardware, but it hasn't arrived yet. Another thing I'll talk about later is Jupyter Hub with a Slurm backend, which has been another great success from this last year. So looking at changes to network coming in the lab, we have 2 diverse 10 gigabit network connections, one to Ashburn in Northern Virginia and one to Atlanta. In 2019, we added a second wavelength to the fibers, so we got 20 gigabits on each link. We're currently saturating this. If you look back at the previous line, chart, you see we top out here. This is actually when you're saturating the link in and out of the lab. So we moved to ESNet 6 protocols last month, and we have a request into ESNet for an upgrade to 100 gig in FY22. That will still leave us going through this third-party E-Lite network, but we're expecting in FY23 we've got a request for dark fiber all the way to Ashburn and Atlanta, so that we can have 100 gig over dedicated ESNet-owned fiber, which will remove the dependency on E-Lite. And all the rack and equipment space is all ready to go for that. So at the moment, we're at a crossroads between JLab's past and JLab's future. In the past, the emphasis was on doing most of the compute locally, and the future is a mix of local and remote resources. So the compute part is successfully negotiated with OSG, and the experience we've had with NERSC. We can now share the peak load computationally across various sites. And this is a key to successful participation in EIC. Storage is more complicated. As we've grown Lustre, we've discovered that it's no longer a good match for some of the high throughput computing workloads. So we started running an XRootD pilot for caching raw data. So you instead of writing the data to tape, pulling it back off tape and put it on Lustre, you cache it behind XRootD. We've also got interest in Rusio to move beyond the file system as a metadata catalog and move beyond this model of everything goes to tape and you have to know where things are on tape. One of the things this would solve for us is we have an issue with millions of small files that get written as metadata in amongst the raw data files, and Rusio will allow us to handle that a lot better. Something that I'll talk about later is that the recent experience with running EIC jobs exposes the need for a better solution for distributed access to data. The emphasis here is that we can't compromise cybersecurity with whatever solution this is. So overall, the key for the future is stepping away from homegrown software solutions, integrating and not creating. And since this talk is going to a wide audience, I'll say that help is always welcome. So drop me a line. Significant accomplishments, Jupyter Hub, which I'll show in a short while, the Open Science Grid. We're now running only Slurm, and we're using it to manage the diverse workflows, for example, batch, interactive, and machine learning. We've increased service reliability, and we've increased our local expertise in OSG services, and a lot of our services are no longer OSG hosted, they're hosted locally at JLab. Okay, I'll skip the rest. So a little bit about the EPSCI group. So we expanded the group to 10 members in 2021. The group's size is going down a little bit now. Some of those members who were actually hired to run on work on data science related topics are moving over to the new data science department. So the group roles are to connect scientific and software efforts across the halls, work on the streaming readout, data quality monitoring, support offsite computing by looking after the software for containerization, software distribution, job campaign pipelines, and so on. And we also have a number of externally funded projects, and I'll touch on some of those in the next few slides. So one of the projects EPSCI is working on is called URSAP, which is Environment for Real-Time Streaming Acquisition Processing. So this is microservices-based design, which is similar to the Clara framework, which is used by Class 12. There are Java and C++ versions of it, and it's under testing, and we've got a paper out on a test that I'll show you on the next slide. We have a lab which is called Indra in the main building at Jefferson Lab. One of the acronyms that was missed out is VTP. So VTP is a card that slits in a VME slot that has an FPGA on it, and it's capable of reading out a VME crate full of ADCs or TDCs over the backplane and pumping the data out on the front panel. So it's an ideal piece of hardware for streaming readout. It's very similar in function to the Felix card that's used at BNL. So we have a VTP data source fed by a programmable pulsar. We take the outputs from a VTP, aggregate the streams, do some online event building, and look at the data rates. And what you can see is that we're currently able to get about 2.5 gigabytes per second out of a single VME crate, which is much faster than we were able to do with the legacy code that we had of 12 months ago. So that part of the project is going very well. And it links into another project called Astra, which is AI-based dynamic detector collaboration. So the idea is that the output from URSAP would go into an AI system that would generate detector calibrations. And that's under testing with gem detectors read out by Stamper. One of the local developments, and again, I'm trying to get away from local developments, but until we find something, we have to write our own, is a data lake that was developed with the help of the PCSci group. The idea behind this is that you want to be able to smooth out network delays and downstream processor component latencies. So you pour the data into a pool and let it sit there and then pull it out at your leisure later. So that this was a software development this year. And we're also working on the transient data format for a streaming readout. So I said that we'd had some success with testing. So we did a beam test in conjunction with Hall B, the Fast Electronics Group, and INFN. The Hall B leader was formerly worked for INFN, and they have this TriDAS streaming system. So we enabled TriDAS components to work with URSAP linked it up to detectors in Hall B, and did a successful beam test in 2020. And there's a paper published in the VCHEP this year on that work. Another project is, and I apologize for the name, EDGE-FAT, is a collaboration between ESNet and JLab on FPGA accelerated transport. So this is an Oscar-funded project to stream data from an experiment into a data center with FPGA processing and data flow steering. So why do we want to do that? So it's obviously to increase the science rate, but it would give you high data rates greater than 100 gigabits per second with a guaranteed quality of service and a dynamic workload balancing via AI and ML, which will support stream data processing and real-time feedback to researchers while experiments are happening. One other object is to explore with ESNet next generation networking fabrics and control. So we have a shared engineering proof of concept between JLab and ESNet. So here's a diagram of what this would look like. On the left, you read out the experiment electronics in a streaming mode. You process it in some computing that's close to the instrument, into a network switch and into this FPGA data shaping system, which tags the data stream with metadata, which wouldn't normally be part of the data stream. So it basically described what the data is, where the data needs to go, but without using the regular Ethernet packet headers. So the data is sent over a network, a high bandwidth fixed latency link, in this case ESNet, but it could just be between a local experiment and a local data center, into a network switch, and then another FPGA system at the receiving end strips off the metadata and makes intelligent decisions about where in the large computing resource the data needs to go. So what you can do with this system is you can look at cluster telemetry, for example, which parts of the cluster are heavily loaded, which ones are lightly loaded, network congestion, and so on, and steer the data to the less loaded parts of the cluster. So this is an interesting looking project. We've got funding for a year to start out on a pilot for this. So there's a summary, which I won't go into again, but I'll let you read at your leisure. We're also working with the AI system that was developed and I talked about last year. So the idea behind this is that we have shift workers who look at dozens of plots a day to ensure data quality. But AIs are now very good at classifying pictures. So Hegner is an AI system which uses models already designed for image classification to classify basically histograms or plots to say which ones are good ones and which ones are bad ones and what the problem is with the detector. It's between 93 and 99% accurate when compared with an expert doing the labeling by hand, and has actually found mislabeling by human experts indicating errors, an error that is expert dependent. So it's currently capable of analyzing images in 200 milliseconds, so it can run tens of thousands of images a day. The focus on this year has been updating the Hydra code. Now we have a data science department with data science experts. We can bring in some of their skills to optimize the code, and also generalizing Hydra to make it applicable to any experiment. There's been discussions with Hall A. We've got training data sets from them to look at using it in Hall A experiments. An LDRD that we have that's new in 2021 is to run legacy code on heterogeneous hardware via surrogate models. So the idea is to make it easy to train a neural net to mimic and replace an arbitrary piece of existing complicated code. So the advantage of this is it lowers the technical barrier to bringing machine learning research into production, but it provides a mechanism to enable a neural net version of an algorithm to run on a GPU, a TPU, or an FPGA without modification. So that would allow you to take a legacy code base and evolve it to a computing center that uses heterogeneous hardware. So the deliverables for the project are a C++ model builder, a tool to identify functions, memory movement, and then auto-generate code to interface the inputs and outputs for the function, and a playbook for identifying promising sites to surrogate in people's code and using these tools as well as existing profilers and analyzers. So that's a new one that started and is kind of exciting. So Jupyter Hub, we've now expanded our use of Jupyter Hub so that basically you can go into the page and you can request machines out of the cluster and have them reserved for yourself. So for example, on the left-hand side, somebody wants a machine for 12 hours. They need 4 CPUs, they need a gigabyte of memory per CPU, and they want NVIDIA Titan RTX GPU. So you can submit this thing, and at some point later, you will get back a shell which gives you access interactively to the hardware that you requested. You can also run this in batch mode to interactively request things to run on GPUs and CPUs as batch jobs. So there's a couple of pictures of it in action, which I won't go into because, well, basically I don't understand what's in the plot, so we'll move on. There are also many other AI and ML projects at the lab. For example, Monte Carlo generator for experimental data sets is being worked on in the theory division. Particle ID for charge pi and polarizability is being worked on. Particle tracking, there are sort of patent applications for cybersecurity for using AI to identify sensitive information in code. So there's a lot going on. There should have been more slides on AI ML, but I'll add those before I post this up for the interest of time. Okay, next one, EIC support. So as Torre said, a major initiative started early in 2021, which was a request for detected proposals and the aggressive deadline of December, which has happily passed and been met by all 3 groups, or so I'm told. So both JLab and BNL were plunged into support of computation related to the proposals, for example, event generation, reconstruction, and analysis of Monte Carlo events. This was an unanticipated and immediate need for compute and storage. Now, from the JLab side, there was fortunate timing because we'd already ordered and had delivered our FY21 compute and storage update, but hadn't brought it online yet. So we quickly changed the plans and dedicated the new resources to EIC. So we were able to dedicate 2,000 job slots and a couple of petabytes of disk space. Now, this was temporarily at the expense of the 12 GeV program, but fortunately at the time the accelerator was down for maintenance, and we were able to fill the hole, let's say, before we needed to start the full run. Now, the lessons learned from the exercise were not a big surprise. The first one is JLab is not BNL. So there were different software tools, different system configurations, but mostly different cybersecurity requirements. The other thing was that the major campaigns require prior warning to compute resource providers. And I think this was one that blindsided us on both the JLab and BNL side, that we were suddenly expected to provide computing resources for the detected proposals. From our point of view, it was useful exercise. Not only did everybody get their work done, but it really helps us focus on our future plans for what we need to do to support EIC.
Ram, you have 5 more minutes.
That's all right, I just finished.
Oh, perfect. Oh, so you had...
So the summary is clearly there's a lot going on, and it's impressive to think that all the hard work this year was achieved despite the non-optimal working conditions, because I'm not really sat in front of a few racks of computing. And I want to thank all the groups who provided slides for the talk. And we look forward to seeing what 2020 will bring, and enjoy your holidays.
Thank you very much for the summary, Graham. It would be great if you add these slides also to the Indico page as a reference, but I guess you indicated that during your talk that you're planning to do so.
Yeah, I asked for a couple more, a few more slides, and they didn't arrive before the time of the talk. I think there were a couple of illnesses around. So once the people have recovered, I'll tag it onto the end of the presentation.
Okay. It of course, one can always update it also on but it's just nice to have it as a reference. But now let's just go to the more exciting part, the questions. The first one is by Torre.
Yeah, very nice, very interesting, just like last year. I wanted to ask about your comment in the context of EIC and doing EIC computing all of a sudden last year, and JLab is not BNL, and I'm interested in can you expand on that in terms were there particular technologies, tools that were different, or particular security requirements that are, so how were they different, and what kind of convergence happened, if any?
So there were two main things. The first one was that we settled on xrootd as our mechanism for distributing data. But we were still in the early stages of xrootd, so the servers were not sufficient capacity for this particular task. Now, BNL were pushing S3 as a mechanism for distributing data. Now, that ties into the cybersecurity requirement, which is one of the key components of our security posture for the clusters at JLab is that we don't allow them to access the internet directly. If we did that, then we'd have to have a lot more patching of vulnerabilities and so on. So the trade-off between increased uptime because you're not patching once a week and having to have basically a softer core and a harder shell around the outside. So quite a few of the issues that occurred were because of data access. The solution to our security posture was to use xrootd. xrootd wasn't really up to it. And jobs ran very well at BNL because BNL has the servers for S3, but the same job didn't run well at JLab and needed a modification. So Jerome and I are working together on as well as the teams at both ends on making that smoother in future.
xrootd has been a workhorse for Atlas for a long time. I mean, we swear by it, and we've had more problems with object stores in S3 than we had with xrootd. So I wonder, are you sticking with xrootd and pushing through the?
Yeah, we're sticking with xrootd. We've got the hardware in order to beef it up. The other thing is that through this exercise, we've learned an awful lot about xrootd and realized it can be used in other places and solve other problems. So one of the examples is the current workflow for the experiments at JLab, sadly, is the data lands on an SSD server, but is then pushed to tape. So when you want to do your reconstruction, you have to pull it back from tape. It would be much better to cache it locally on disk, but then you need a cache management system, and xrootd can actually solve that problem for us. It could be the cache manager.
Right. Okay, interesting. Thanks. Thumbs up for me for xrootd anyway.
Are there any more questions to Graham? Yeah, Wouter, please.
Well, I guess I'll ask the same question I asked Torre. So I saw you mention a number of acronyms, you know, ERSUP, EdgeWrap, whatever it was, Hydra, which is probably not an acronym. None of them at this point have any kind of web presence beyond, you know, the link to VChap or a link to a GlueX wiki. What's JLab's approach towards making this available as sort of community tools rather than something that gets used in-house? And when you gave the example of of expanding use, it was from Hall D to Hall A within JLab, not necessarily outside.
Yeah, so that's a very good question, because it's one that we're trying to wrangle with the answer to. We would like to go in the direction of community tools, but some of these things like Hydra and certainly the ERSAP and so on do not exist out in the community. So we have to, as you say, have some sort of presence to push that out and let people know, hey, this is what we're doing. And I'm really open to suggestions on how to do that. Which group to join that would be appropriate and that sort of thing. But we do need to do that. We need to let people know what it is that we're doing that's unique. But on the other hand, we need to learn what other people are doing that we don't really need to replicate.
Thanks.
Offer?
Hey, Graham. Great talk. Really interesting. I just had a question about your Jupyter hub. What are you doing in terms of account access for that? Is it people with JLab accounts that are able to access it? And what kind of usage have you been seeing? Is it mostly local people? Or?
That's a good question. It's not, I don't think it is restricted to JLab. But I do not know off the top of my head what the access mechanism is. You
need access to the JLab SciComm farm. If you can submit a job there, then you can use it.
Okay. That's going to be my next thing. Is anybody on the line who knows? Right.
Yeah, David just answered.
Yeah.
So
okay.
You need to have a Jefferson Lab account which allows you to access the farm, and then you can use it.
Are there any plans to do any kind of federated access to it, or is it too early to talk about that?
We're already planning federated access with EIC, and it looks like the mechanism that we might use would also be usable by other groups, but we'd have to look into that. It's right on the start of trying to look at federated ID.
Great, thank you.
One more question by Wouter.
Yeah, this is just a comment on, since we're talking about Jupyter Hub, I think it's useful to point out that Jefferson Lab has had this Jupyter Hub in some form or other now for, I think, 4 years or so. And I would argue that has been important in getting some of these machine learning initiatives started early. So it sort of displays in how a lab can be on the leading edge of adopting some technologies and thereby sort of encourage development of a research program. So I really think that was an excellent idea by the JLab computing scientific computing group at the time and security group to set that up and to be open to that.
Thank you.
We have time for maybe one short question or comment. I don't see anything up. So thank you very much again, Graham. This was very interesting. Pleasure to listen to your talk. Thank you very much for doing this. The third contribution today will be by Benedikt Hegner. He did his PhD at DESY, where he studied the spin of the top quark. And then about 13 years ago, he joined CERN. And at CERN, he has had various coordinating roles in the CMS experiment, mainly analysis of CMS, but he also has been involved in scientific computing software for Bell 2. And he will talk to us today in his role as a member of the coordinating team of the HEP Software Foundation, and he will give us an update about what happened all this year in the HEP Software Foundation. Benedikt, we are looking very much forward to your review. Would you like to have a 5-minute warning during your talk?
Sure, you can give me a 5-minute warning. I however hope to really stay on time.
Okay.
So I hope you can see my slides.
Yes, confirmed.
Perfect. So we'll just, I'll just summarize for the HSF a few of the highlights of last year. And I would like to start with a disclaimer. So the HSF is a forum for people to communicate, to exchange ideas, to work together, but we do not own or distribute resources. So we just help projects and people to come together. So every successful project and every successful effort I'll mention in the following slides is just owned by the people who do the work. So if I'm talking about highlights of the HSF, I'm talking about a lot of great work done by others. So just to be clear about that. So let me come as a little reminder to the HSF organization. Well, we started as a bureaucracy, and we are just trying to do things as lightweight as possible with very little structures. So we have a coordination team which gives a little bit of oversight and drives the overall direction and helps in all organizational matters. This team is, I would say, quite small. There are a lot of motivated people there. And we have, just to make sure that voices are heard, we have as well ex officio members from experiments and some stakeholders of WLCG. The important thing about the coordination team is it's an open team. So if someone is interested in putting in effort, this person is very welcome to join. Then we have more focused working groups. And at the moment, we have a working group on event generation, on simulation, reconstruction, and software trigger analysis frameworks, and tools for building and software distribution. And then we have training, and last but not least, we have the Python and app working group. And as I already said, the role of HSF is just as a meeting point of information, and so on. And what we try is always to motivate people after having discussions, actually make all the discussion public, make it, write it down for the future. So whatever has been thought can be used in the future again. And just to emphasize a little bit the importance HSF had in the last years, we all know that 2021 was again very complicated with all the pandemic going around. So we had no in-person workshops, no in-person meetings, which means no informal coffee chats, no ad hoc discussions, all that what usually is very important, we just didn't have. Now, within all the collaborations, we are pretty used to remote and distance working, and we sort of have the collaborations organized around this for many, many years. Nevertheless, if you're new to a collaboration, it's not easy to start in this environment. But once you're started in there, I think all the collaborations know rather well how to do things. Now, once you leave this boundary of a collaboration and this well set up system, things are much more complicated. And for this, we always relied on, as I said, conferences to synchronize and to meet, to exchange ideas. And despite all the efforts by the organizers, virtual events like the VCHAP or the ARC last week, they cannot replace this feeling of being in person. And my claim is that having an established forum like HSF, where we can create and exchange ideas without meeting physically, was very essential to stay productive in 2020 and in 2021. And I would say already this is a highlight for the HSF of 2021. And this roundtable we are now attending to played as well a very important role there. Now, Let me come to some of the more formal things. At the beginning of the HSF, we wanted to define a little bit the common goal and the global vision for software and computing. And we created a community white paper, which we published in the Computing and Software for Science. And we had more than 300 authors, more than 120 institutes, and plenty of material. That was, however, quite some time ago. So last year, we updated some of the chapters of the white papers, and we made sure that all what we learned in the first publication actually went into it. And now we just finished this year the review of the high luminosity LHC preparations in the LHCC. And here, based on all the history of setting up the global vision and so on, the HSF had a very important coordinating role, and all the notes, documentation, and so on will be made available on archive soon. And what you can see is that the HSF continues to be recognized on the international stage. So in the ICC, we are frequently invited to give talks. For example, Snowmass and the small experiments workshop was a place, and that's actually something I'll come back to later again. Now, one of the working groups where I really think we are really, which really excels is training careers group, because many of the skills you need these days to do research are in software development or in using software. And essentially, a lot of these things are very common to all of the collaborations, all the projects, and a lot of material has been created in the past. And what now the working group did was essentially taking up the LHCb starter kit and making it grow, making it bigger, and making it more useful for the entire community. And we now have the training group running software carpentry workshops. We have very successful C++ training courses, and we are assembling a complete curriculum for training in HAP based on all the software carpentry templates. So the idea is really to provide everything you need for training in our field to make sure that things are there, everybody works together, and even to make it easier to switch between collaborations if you have similar kind of knowledge, and as well similar kind of conventions you're learning all this. And all this has been nicely summarized in the paper about HAP software training challenges in the CSBS. And the publication is actually based on a very nice plenary presentation of VCHAP. Now, another very successful group is Python and HAP. And we had a lot of PyHAP workshops. And it all started in 2017. We had the analysis ecosystem workshop in Amsterdam. And there, first time, actually, we managed to write down that Python should be treated as a first-class citizen when it comes to data analysis. And this and other discussions inspired the first PyHAP event at the CHAP 2018 in Sofia. And based on this, we had very successful follow-up workshops in 2020 and 2021. And for the last one, more than 1,300 people registered, which is really a lot, given the size of our community. And there have been a lot of trends and hot topics, and one is automatic differentiation. We had many of the talks and tutorials done as notebooks, which is sort of the state of the art at the moment. And doing it this way means that people could either live or after the workshop actually use the material. And all what has been done in this PyHAP workshop is now being uploaded to the YouTube channel of HSF, even with captions, which is really great. So if you're interested in anything, this group is really making sure that whatever is being done can be used even after the events are over. Now, coming, since I did not want to spend too much time on the entire presentation, let's come to a few highlights of some of the working groups. For example, the Reconstruction and Software Trigger Working Group. People at CERN have been very busy with actually getting the software of the individual experiments ready for the next run. So there was not that much activity in common software writing, common projects this time. But what happened was making sure that we get a vision for what we want to do once things are in place for the next run. So the group carried out a survey to define the topics, not for this, but for next year. And based on the results, and I linked here as a summary for that, they now plan multiple mini workshops. And actually the first one already took place, which was a very productive discussion on 4D reconstruction, which just means reconstruction, including timing detectors. And that will be a very important topic for coming experiments. The analysis working group managed to, for example, send up standard candles for analysis so that comparing different solutions, one actually has an idea how they compare if one does it end to end. How easy are things to be done, just not trying out a little toy, but really a full thing? How easy is it? How fast is it? And I think having established these standard candles will really help in the future. Another topic in that group was a very long discussion on metadata and analysis. And that really spawned multiple months of fruitful discussions, of sometimes a little bit controversial discussions, but everybody was really trying to get a nice outcome there. And we now have a paper, again linked, which is waiting for full publication. So it's really worth giving it a read. And the frameworks working group, we actually heard about it already today. That the highlights there was the Dune Framework Review. And I think it was just a great example for the collaborative spirit in the field, because everybody contributing there did it just in the free time. It was not a paid thing. It was just everybody was interested in doing this, and people really spent a lot of time. And I think the review was as well quite a good learning exercise for the entire community. Now, coming to two more groups, one is the development tools and packaging. And the highlight there is that we really now have a very strong connection with the spec community and Lawrence Livermore. And we actually had the original author of spec, Todd Gambling, coming to one of our meetings, and we had a nice discussion. He was explaining a little bit his vision. We were trying to explain what the special needs in our community are. And he will certainly come again to one of our meetings. So I think that's really a highlight that we now manage to connect with our packaging and building environment to non-high energy or non-nuclear physics fields. So we really managed to get the bridge done there. And coming to another group, which is simulation. There's really a lot of effort going into understanding the potential of machine learning. And there was as well a lot of work going into trying particle tracking on GPUs, which obviously is a very challenging task. And we have now multiple projects trying to tackle it in different contexts. For example, ADAPT is one of the projects which sort of more happens on this side of the Atlantic. The Celeritas, which is a DOE-funded project, or Optics, which is yet another project. And I'm really looking forward to see how these things evolve in 2022. There was as well a lot of work done together with the Compute Accelerator Forum, and you can see on the latest slide a little summary of that. Now, another group which I think is very productive and actually very essential, because we have been in the past not that good on that field, is event generators. Because it's the base of all the simulation. And so far, it was not that important of a topic when it comes to the overall CPU budget. But now with the precision in the future runs of LHC, it becomes more and more important. It will become more and more significant in our CPU budgets. So we really have to put an effort into that. And we had essentially 3 years ago, we had a big computing for event generators workshop. So it was in 2018. And the working group then was created based on this. And today we have really a nicely working community. We had a very great talk in the LHCC, and I linked it here. And we as well there have a CSBS paper, which again, I think is worth reading. And this is again an example where within a short time, we managed to get the community really nicely working together after many, many years of sort of only some ad hoc interaction. Now, another thing which leaves us a little bit out of the concrete work of the working groups, which is lobbying. So the HSF has been helping a little bit in providing letters of support for various projects, and I give a list here of things which happened in the last few years. So I think HSF played a role in getting community work started and helping community projects to find funding. So to create the spirit in the community helped to have all these projects popping up, and we are now happily collaborating with all of the projects listed here. Then, as already mentioned a little bit earlier, there's a Compute Accelerator Forum, and this essentially focuses on extreme parallelization and non-CPU architectures. So how do we take advantage of all the heterogeneous computing? And there have been a lot of great meetings about it, and there are projects like Alpaca or Cocos were nicely presented. What are the reconstruction issues in the various experiments? Can we do proper detector geometry on GPUs, which as well was the topic of the simulation working group? What do we do about FPGA programming? Again, simulation is the use case. And how do we actually make things work in terms of infrastructure and the availability? Then, as one of the last things to report on about 2021 is the Google Summer of Code. And since about 4 years, we have been an umbrella organization for the Google Summer of Code, which means HSF together with CERN was sort of the communicator between our community and Google to make sure that we get the projects funded and so on. And this year we had 19 participating organizations, so labs and universities, and 70 projects. And in total, we got 25 students joining the teams. So 25 people just being funded by Google to do great stuff for us. The final reports I linked to here. And the good thing about the Google Summer of Code is that usually you have very talented students. So both the skill and the motivational level is very high. Sometimes you have a little bit of strange submissions, but you have a selection process. And usually after the selection, what you get is really, really good. So if I'm allowed to compare Google Summer of Code students in the field of software with the CERN Summer Student Program, I would for sure always go for Google Summer of Code student. And the nice thing there is this Google Summer of Code is always a chance for you to try more experimental developments. If it fails, it fails. But if it's successful, you really manage to try something out. But as many other HSF activity, everything suffers a bit from a CERN bias. And this is not because all the CERN people try to get CERN stuff into, it's just the result of missing project proposals from other fields. So if you have a good idea for, okay, I always wanted to do this and that project, but I never managed to have time, write it down and submit it to the Google Summer of Code. And we'll have a call for the HSF going out rather soon. So just keep your eye open. And once the call is there, feel free to propose a project. Now we as well had some gaps in this year. And as already mentioned twice, the HSF remains to be dominated by LHC-centered efforts. This partially reflects just the size of the community. I mean, the LHC community is just much bigger than other parts of the community. Nevertheless, small experiments would benefit quite a lot from all the developments which have been done. And a lot of these things are not out of the box, but almost out of the box solutions people can try to adapt. For example, training is one of these things, packaging in particular with spec now is one of them, and you will certainly find others as well in reconstruction or simulation. Now, what we have to do is we have to do better on providing things for non-LHC communities and involving non-LHC communities. And just to give you an example for one of the things which could be useful for non-LHC experiments is Key4HEP. This is just an idea to create a software stack which can be used out of the box. So have a look at it. And if you have any idea how to improve or change things, you can contact the developers. Now, I would already conclude here on my highlight presentation. So the HSF is a place for international efforts and cooperation. And we are, in particle physics, an international effort with a very excellent tradition of cooperation in many different domains, detector R&D, experiments, and so on. But still, we have a lot of incoherent approaches, duplication, and so on. And at the HSF, we try to support and foster common projects just to avoid incoherency and duplication. And doing this, I think we encourage a lot of diverse R&D, just trying out new things before just doing something. And we see now a real success in attracting funding. You've seen the list of funded projects I mentioned before. And we have a lot of recognized links to other main players. And I think the HSF offers an excellent place to present your work, to discuss successes, as well as disappointments, because we are not only interested in here to hear what works, but it's as well important to know what didn't. And it as well offers a place to help leading the community activities in a proper direction. And if you are interested in helping in leading the efforts or steering a little bit, we are still welcoming working group convener nominations for next year. I've sent out a call. So if you have a great idea, please let us know. And that concludes my presentation for today.
Thank you very much, Benedikt. This was really very interesting and also inspiring what you're doing. And you absolutely kept up with your reputation that you stood on time. So I could not even give you the 5-minute reminder because you were perfectly on time. This allows quite some questions. And the first one will be from Torre.
Hey, Benedikt, very nice. Thanks. I have a couple of questions or comments. First on Key4HEP. Last month, you guys in CERN EP had an R&D meeting, and that included a session with an EIC focus, and within that software computing discussion. And from our side, we talked about the East simulation project as a point of possible common interest. And from your side, you talked about Key4HEP, EDM for HEP, which sounded really interesting to me. And I know it's interesting to EIC colleagues, Argonne folks, for example, worked a lot on Key4HEP type functionality. We had long discussions about event data model, common event data model, prior to getting immersed in proto collaboration work in the EIC. And just to flag that it seems to me it would be a very interesting area to explore and discuss Key4HEP, EDM4HEP type topics as we hopefully talk next year about common ground on EIC common software in East and all of that. And let me just add one more comment that in mentioning EPSFT, of course, I don't equate HSF and EPSFT, but I do want to mention what probably doesn't get mentioned enough, that for all that HSF is a duocracy and doesn't own or control any resources and depends upon volunteers, it also depends upon the bosses of the volunteers letting them work on HSF. And EPSFT in particular in our community has been absolutely fantastic in having extremely talented people spend large amounts of their time on HSF to the great benefit of those of us who value HSF. I only wish, for example, that we were able somehow to support somewhere such people over here in the US. So kudos to EPSFT for that, and I'll stop there.
Thanks, Torre. I think the kudos you have to give to Pere, but the EIC, I think it's definitely an important thing to follow up on, because just to make sure that we do not accidentally fork off new things, and to make sure that whatever is being created actually makes sense for everybody.
Mm-hmm.
Are there more questions for Benedikt? Well, maybe waiting for one or two more questions. I just would like to make the HEP Software Foundation the complement to being really welcoming to the nuclear physics community. So you made this comment about this gap between the LHC experiment and other communities, but regardless if we joined any kind of working group meetings, like for instance, as example, yesterday, some of us were in the training working group to learn a little bit what we could do together on training efforts, or being it like joining here the software and computing roundtable, which started with a nuclear physics focus and now is HEP, NP, and maybe more. I think this is very nice. So thank you very much for being welcoming to other communities. Are there more questions?
Let me mention that I was really struck by your comment that given a choice between a CERN summer student and a Google Summer of Code student, you'd pick the Google student every time. That's a striking statement, because CERN students are really good. So Google Summer of Code students really must be good. So it is good to be reminded that the only reason that that program is a bit CERN-centric is, as you say, because the proposals are kind of CERN-centric, and we are as welcome over here to put in proposals as anyone.
Yeah, exactly. Whenever you have an idea, please submit it. And what I want to make sure about the CERN summer students, the reason why I would take the Google Summer of Code ones is the skill set, because we get summer students which are mainly physics centered, and the Google Summer of Code students are usually software and computing centered. So it is as well a function of the education people receive at the university. And that's one of the things which I hope will be solved in the not too far future, that actually part of the curriculum really becomes a good data science knowledge. But so far, it's not commonplace.
Mm-hmm.
Any more comments or questions? There is one by Wouter. Wouter, please.
Yeah, so I don't have my question from the previous that I asked the previous two speakers, because obviously the HSF does an excellent job at reaching out. But I do have a sort of a question to maybe the BNL and the JLab community here. So you did mention that HSF is a little bit CERN-centric, LHC-centric, and thereby maybe a little bit European-centric. There's some links that you pointed out, in particular DOE, CCE, IRIS HEP on this side of the Atlantic, and I'm wondering. I think Torre mentioned a couple of points where DOE, CCE, and IRIS HEP were points of connection with what BNL is already doing. In the JLab presentation, I don't know if that was as clear that was included as well, but could the labs on this side of the Atlantic do a better job of working with those organizations, or is working through the HSF a sufficient pathway? I know there's issues related to the separation of funding in nuclear physics and high energy physics in the US based system. So maybe this is just simply not as easy to imagine. So not really a direct question, I guess.
Well, I think it's an interesting comment, which is also not so easy to comment on. I would just leave it as some remark at the end, which is, I think, something to follow up over the course of the next year. But I mean, what I can say is part of the software and computing roundtable. I mean, all the purpose which we have here is strengthening common software initiatives, bringing people together, and I think we made quite some progress when we started the software and computing roundtable at something which was Jefferson Lab only. Then it was really exciting to see that our colleagues at Brookhaven joined, and this also, I think, manifests itself in common work which is happening, mainly EIC related, but I expect this to grow. And then now also the growing and grower connection to the HEP Software Foundation and related communities. So I think I would say what you mentioned here is very interesting, and but it also is more or less there. We are organically growing, and there I think that there is on all sides the interest in identifying common projects and working on them. Graham, Torre, would you like to add anything here?
Well, I'll say at BNL, you know, our management has been supportive at BNL for various HSF roles we've had over the years, taking small pieces of people's time, and you know, we probed early on whether we could actually get a substantial amount of support to actually designate somebody as working a substantial portion of their time on HSF, and that doesn't happen because of the usual budget pressures. It just highlights how nice it is when it does happen, like in EPSFT, as I mentioned. And there are the organizations within the US specifically charged to collaborate cross-experiment, both of them with the HEP orientation, IRIS HEP and HEP CCE. IRIS HEP in particular has very tight connections to the HSF. Just to express an opinion, from my point of view, it would have been ideal if one or both of those projects would have designated a person or half a person as, okay, you're our HSF person, and you're going to work on the HSF with HSF people and HSF projects. We've never gone that far in the US, and I think we would benefit if we managed to find a way to do that.
Does this answer your question a little bit, Wouter?
Yeah, it does. I think I think I'm just looking forward to. Okay, sorry. Let me start again. I think, Marcus, you're right that with the software and computing roundtable, we've had excellent speakers from the HSF, from IRIS HEP, and so on. I think I just would like to see that go more in the direction of joint projects and not just exchange. But yes, Torre explains very well why there's issues that why that's not so easy.
But I'm sure that when we repeat this meeting end of next year, that that we will be further in this direction and maybe already have some joint project. Let's stay optimistic here. Let me thank again to conclude here all the speakers. This was really exciting and this was really interesting. Thank you so much for preparing the talks. Torre for the BNL update, Graham for the JLab update, Benedikt for the update from the HEP Software Foundation. And thanks everyone for staying long. So this was today a little bit longer, but we had quite some interesting questions, quite some discussions. So I didn't want to cut this short. Part of this is here to have a discussion forum. So thank you very much. We will have a break in January in the Software and Computing Roundtable, and we continue on February 8th with a Software and Computing Roundtable on programming languages. So stay tuned for updates for the exact agenda, what will be the presentations, what will be the speakers. And so at this moment, thank you very much for attending today, and thank you very much for making the Software and Computing Roundtable this year a success by joining our meetings and asking interesting questions and raising good points. Thank you very much.
Thanks, Marcus. Bye.
Bye-bye.